In part 1, we covered definitions and the correct notation for those definitions. In part 2, we're going to start to cover the rules of geometry. If you think of geometry as a game, postulates are the rules that you have to follow. In order to come up with a rule, it must work every single time. Our first postulate, our first rule, is the ruler postulate. It says that if we have a line segment, that line segment has length, and we can measure that length. In order to measure that length, we're going to use a device that always marks off the same length, that same distance, much like a ruler. This same length every spot is called a one-to-one correspondence. To find the measure of segment AB, we put a ruler next to segment AB. If we look, B is at 11 and A is at 4. Now that does not mean that AB has a length of 11 or 4, but this postulate allows us to use those two numbers to find that length. The notation for measure is a lowercase m followed by whatever we're going to measure, or just two letters AB written in italics. It's tough for me to draw italics, but if I were to type out AB in italics, you'd be able to tell that this is in italics. Your book often will use this notation. I will try to stick to this notation. To find that measure, we need to use these two numbers. How do we find length between two numbers? How do we find distance between two numbers? Similar to the slope formula, we're going to subtract those two numbers. 4 minus 11. Now many of you are saying, why did I take 4 minus 11? Well, I need to come up with a rule that works every time, not just when I take 11 minus 4. The distance from A to B has to be the same as the distance from B to A. This postulate has to work whether I go from 4 to 11 or from 11 to 4. When I do this math, I get -7 or +7. But this length is going to be positive. Length is always positive, so how do I make this negative number positive and keep this positive number positive? The answer is absolute value. In order to find the length of a line segment with a ruler, I subtract the two endpoints and take the absolute value of that answer. That way, whether I get a negative number or a positive number, I'm going to always get a positive length. Many of you might also ask, why didn't I just scoot this ruler over so A was at 0 and then find out that B was at 7? Well, essentially, I'm really doing this formula where one of these numbers is 0. Since this has to work with any example, I have to come up with this formula, not just when A is at 0. Postulate 2 is the segment addition postulate. It allows us to add segments together. Now when we add a segment, like segment AB, to segment BC, a segment plus a segment is going to give us a bigger segment. In this case, segment AC. And that makes sense. A segment plus a segment is going to be that bigger segment. To find out how long AC is, I'm going to make one subtle change here. Right now, this is written as AB. From postulate 1, I can figure out the measure of AB. Right now, this is segment BC. From postulate 1, I can find the measure of BC. And right now this is AC, and I can switch this to the measure of AC. This doesn't seem like a big change, but the segment addition postulate allows me to go from a segment to its measure. This is a geometric figure. The measure is a number. So I can switch from a geometric figure to numbers. So if I measure AB, let's say I get 10, I can replace this 10 with the measure of AB. And let's say I measure BC and I get a length of 5. I can replace the measure of BC with 5. Now I can add these two numbers. And the measure of AC is going to be 15 long. It's going to be the length of these two segments added together. This seems like a lot of work, but it's a good introduction to what we're going to cover later on when we start to talk about proofs. Similar to postulate 1, postulate 3 allows us to measure angles. To measure an angle, we're going to use a protractor, and we're going to measure our angles in degrees. Here we have angle DOA, or angle AOD. To find its measure, I'm going to take my protractor and put this point right on the vertex. And then find out what angle each one of these rays is at. If we look at ray OD, it is at 61, 2, 3, 4, 5, 6, 66 degrees, and ray AOA is at 21, 22, 23, 24, 25, 26 degrees. To find the measure of angle DOA, I'm going to use the notation for measure, the notation for an angle, and then I'm going to name this angle with 3 letters, DOA. Again, O is that vertex. And similar to the ruler postulate, I have to come up with a way that works whether I take 66 minus 26 or 26 minus 66. 66 minus 26 is positive 40. 26 minus 66 is negative 40. To make sure that my answer is always positive, since this measure is going to be positive, I'm going to have a positive number of degrees, I need to take the absolute value. That way, no matter which way I subtract, I'm going to always get a positive answer. Similar to the segment addition postulate, postulate 4 allows me to add angles together. If I look at this picture, if I add angle LAM and angle MAN, those two angles together give me the bigger angle LAN. An angle plus an angle is an angle. Now I can take those angles and measure those angles. That subtle change by putting this M in front of all of these allows me to go from the geometric figures of angles to numbers. And in this case, those numbers are going to be in degrees. If I take a protractor and I measure angle LAM, and I get 32 degrees, I can substitute in 32 degrees for this measure. If I take a protractor and I measure angle MAN, and I get 36 degrees, I can substitute in that measure for this angle. Now I can do this math. 32 degrees plus 36 degrees gives me 68 degrees. So the measure of angle LAN is 68 degrees. Again, this seems like a lot of work, but it's a good introduction for you to see what a proof is going to look like.